All right, let's talk about the biggest question there is. How does it all end? Not just a show, not just a civilization, but everything. The entire universe. And today, we're diving headfirst into one of the most, well, apocalyptic theories out there. The Big Rip. I mean, it's a question we've all probably wondered about, right? Staring up at the night sky. For cosmologists, though, this isn't just philosophy. It's a genuine puzzle they're trying to piece together with some of the most mind-bending physics you can imagine. Is the universe going to fade out? Is it going to collapse on itself? Or is something way more violent in store? Okay, so here's the deal. The biggest clue we've got in this whole cosmic mystery is, well, it's a strange one. For the longest time, we all figured gravity was putting the brakes on the universe's expansion. Makes sense, right? But then, in the late 90s, observations of these super distant supernovae just blew that idea out of the water. The universe isn't slowing down at all. It's hitting the gas. It's accelerating, pushed along by this invisible, mysterious thing we've nicknamed dark energy. And that acceleration, well, that's where things get really wild. It opens up some seriously extreme possibilities. So for this explainer, we're going to be cosmic detectives. We're going to investigate the most wanted, most extreme suspect for the end of everything, a scenario called the Big Rip. So let's really set the stage for our investigation here. When we talk about the ultimate fate of the universe, what are we even trying to figure out? Yeah, and I gotta stress this isn't science fiction. This is a super active area of scientific research. But we are absolutely at the frontier of what we know. We've got clues, we've got some pretty solid theories, but the final verdict? It's nowhere in sight. So think of this as us exploring the possibilities, not reading from a settled textbook. All right, time to meet our prime suspect. What in the world is the Big Rip? And yeah, with a name like that, you know it's gotta be pretty intense. So this is how it would go down. And it's not like one big explosion. No, it's this methodical, almost terrifyingly orderly deconstruction of everything. First, the expansion gets so powerful it rips apart huge clusters of galaxies. Then it comes for individual galaxies, like our own Milky Way, just torn to shreds. But it doesn't stop. The force keeps growing until it's stronger than the gravity holding our solar system together. Earth would just fly off into the void. And in the final, frantic moments, the force would become so overwhelming it would tear apart planets, you, me, and eventually the atoms themselves. Everything gets ripped asunder. You know, this quote just nails it. Think of the fabric of space-time itself as that rope. And this phantom energy we're going to talk about is just pulling and pulling harder and harder exponentially until every single thread gives way. Even the fundamental forces holding the nucleus of an atom together, snap. It's a complete unraveling of reality. Okay, a cosmic crime this big needs a culprit, right? A murder weapon. So what could possibly be powerful enough to drive something like the Big Rip? And here's where we get into some really wild theoretical stuff. The culprit has a fittingly spooky name, phantom dark energy. See, in our standard model, we kind of think dark energy's density stays constant. But what if it doesn't? What if, as the universe expands, the density of dark energy actually goes up? So more space means more dark energy, which makes space expand even faster, which creates even more dark energy. You see where this is going. It's a runaway feedback loop, a runaway acceleration. That's phantom energy. So how do scientists even tell the difference between regular old dark energy and this phantom menace? How do they hunt for it? Well, the whole case, the crucial clue, it all boils down to one single number. A parameter that cosmologists just call W. And this breaks it down perfectly. Think of it as two different paths the universe could take. On the left, you've got the standard theory, the cosmological constant. Its density is stable, its W value is exactly -1. That path leads to a slow, cold, quiet end called the Big Freeze. But on the right, that's our suspect, phantom energy. Its density grows, and its W value is less than -1. That tiny little mathematical difference means a completely different and way more violent ending, the Big Rip. So this is it. This is the whole ballgame. The entire fate of our universe, trillions of years from now, could hinge on whether this one number is exactly -1 or if it's something just a tiny bit smaller, like -1.1. That's the trigger. That's the difference between a quiet fade to black and a cataclysm that shreds reality itself. So the Big Rip is a lot. It's a terrifying possibility. But a good detective never gets tunnel vision. We have to look at the entire lineup of cosmic suspects. So while we've been zeroing in on our prime suspect, the Big Rip, there are really two other classic scenarios that cosmologists have been kicking around for decades. Let's put them side by side. Okay, this table is basically the entire case file. You've got our Big Rip, driven by that crazy growing phantom energy. Then there's the Big Freeze, also called the heat death, which is driven by that constant dark energy. Right now, that's what most scientists think is the most likely outcome. And then you have the old classic, the Big Crunch, where gravity would someday win out and pull everything back together. But since we see things speeding up, not slowing down, the Big Crunch is looking pretty darn unlikely these days. So really, the main event is the freeze versus the rip. Okay, so we've reviewed the evidence, we've met all the suspects. What's the current verdict from the scientific community? Have they cracked the case?
The short answer is nope, not even close. The case is still wide open. See, the evidence we have that accelerating expansion is a massive clue, but it's kind of like finding a footprint at a crime scene that could belong to two different people. Our measurements of W are really, really close to -1, but there's still a margin of error. And that little bit of uncertainty is just big enough that we can't rule out a value that's slightly less than -1. And that means we just can't say for sure if we're headed for a freeze or a rip. The mystery continues.
Now, if, and it's a huge if the Big Rip is our future, when would it happen? Well, some physicists have run the numbers, and one popular calculation puts it at around 22 billion years from now. But please, do not mark your calendars. This is 100% a speculative guess. It all depends on the true nature of dark energy, and that's something we just don't know yet. And that leaves us right here, staring at one of the biggest, most fundamental questions in all of science. A rip, a freeze, or a crunch? Will the cosmos be torn to shreds in a violent finale? Will it slowly fade into a cold, dark, empty silence? Or could gravity somehow make a comeback and pull it all back together? The truth is, we don't know. The cosmic detectives are still on the case, and the final chapter of the universe has yet to be written.